Hi, I'm Robert Shivas. I'm from VarioScale, and I'm presenting the advances in the VarioMill prep system here at ISTFA 2016. Two things we want to emphasize is this is a production quality tool, as well as an advanced tool for ultra-thin prep to micron remaining thickness. The VarioMill, in review, is a 5-axis CNC tool. We call it a true 5-axis because the stages are continuously tipping and tilting as it's following the contour of the die. This is generated as an embedded toolpath, fourth-order polynomial fit to a small data set of points, not a large array of discrete points. We have the automatic tool exchange that keeps us production quality, the automation. In situ measurement then tracks the surface and the thickness changes as you're thinning. You can make the adaptive polynomial changes as you need and go back to correcting the grind. Because we have the true 5-axis motion, we have fine precision grinding, allows us to have high throughput. One factor in that is we only have one-step polishing at the end. We hate polishing, don't want to do it, it's all in the grind. The Ultra then is reliably processing below 3 microns of RST. On the left-hand side, you can see the fine precision means the RMS of the as-ground surface is only 30 nanometers. The peak to valley is 300, so you're removing less than a micron, 0.3 to 0.5 microns of material to get to mirror surface finish. Like we said, one-step polishing. We've got a data set from the Viz spectrometer at 2 microns, plus the Viz image through that chip. It's all green, which means it's very thin. And at the end, you've got the final polish at 1.2 nanometers of RMS, optical finish. What we want to show is this is interactive back and forth between the mechanical side and the optical side. The red circle represents the imaging. It's the NIR and Viz dual source LED for imaging. The orange circle is the NIR spectrometer, which is the traditional way to measure silicon, transparent above band gap, from full thickness to about 5 microns. And then the green circle represents the Viz measurement system to get below 5 microns. On the right-hand side, you've got the mechanical system, 50K RPM, spindle, automated collet for a tool exchange, water cascade, the blow-off routine, and the slurry pours for polishing. The water is recycled and continuously filtered, so you don't need wet lab space in order to own this tool. And the way it works is that you do some grinding, you'll check it with the measurement system, it'll go to the left-hand side, measure, update the poly, back to the right, and then you can continue to process iteratively from there. This allows us to adapt to the change of shape as it's being ground and being thinned. Stress relaxation occurs, change the poly a little bit. So we don't want to lose sight of the fact that it's a production level tool. We can take a large die like this Opteron here, it's 17 by 16 millimeters. It's an old style, it's huge. And we can process it down to 50 microns for optical probing in 4 slices here. That takes about an hour. Right, first cut is 600 microns off the top. Your accuracy to the target is 5 microns, and your plus or minus 2.7, which leaves you within spec in most applications, the 90% application. With a few cuts and some measurement updates to the poly, your final target accuracy is 0.3 microns to target, and your range is plus or minus 1.5 microns. Now that's 3 microns of total thickness deviation over 17 millimeters. So that's 1 in 6,000. And we want to show is compare that to a standard, a new technology, an Atom processor that's 14 nanometer technology. It's 8 millimeters on the side, so this only takes 20 minutes to process as grinding, 20 minutes as polishing, and you should realistically be running through a chip an hour with this tool on these size die. But that being said, we also want to push the limits of the ultra thin to 1 micron and below. So we say we can reliably process global silicon to 3 microns, region of interest 1 micron, and we presented a paper this week where we showed it's electrically non-invasive above ring oscillators at 1 micron. What we want to also talk about is when you get below a micron, you end up encountering the topology of the circuit layer. So you say, what does it actually mean to be a micron above the surface? On the left-hand side, you can see as you march the focus spot size across the pad there, you're at 1.2 microns of thickness, or when you're away from the chip, you're at 1.5. But if you're on the edge, you get both signals. So be careful with that. You can see the C4 warpage from the stiffness change when the C4 bump balls are in the package. But we have the tool that can measure sub-micron silicon thickness. Right? Example here is at 0.45 microns. You've got good modulation still, nice clean signal, and you're actually imaging that point. It's transparent silicon at 0.45 microns. So we say, what's next? Ultra thin, ultra planar, singulated die. That's what's next. We're going to take this, leverage the current mill platform to the next generation tool. We're going to be ultra planar deprocessing singulated die, take them off the package or have them depackaged. And we're going to slice from the backside the metal layers 1 through 14. We'll need a an order of magnitude stiffer stage to do this at 100 nanometers stiffness. But that's what's coming next for the mill. Proof of concept then is the Atom processor has been depackaged and put on this plate to be processed. So as the time expires for the presentation, I'll leave you with 2 videos on the automation of the tool. On the right-hand side, you can see it's been grinding and doing an air blow-off right now to prep it for measurement, making sure it's dry for measurement. And then it will go from the grind side to the optical side to do the measurement. On the left-hand side, what it's been doing has been tool exchange. So it went from a grind tool, handoff to the magazine. It's going to pick up a polishing tool and detect, and then it'll go to the polish straight away. So not only is this, you don't need the end user interface with this. You can free up a tech to do something else, but it's also throughput increase. You've got your automation down. And yeah, when you iterate this measurement on the right-hand side, the computer then generates the polynomial fit. You update the polynomial, and you can start grinding right away. You don't need to have any interaction to dry off the chip or to do any processing like that. So that's a presentation. Thanks. Hope to see you at our booth.